Hello, everybody. I'm going to talk about a couple of short topics today. One is the Hamiltonian for molecules. So we're going to start with the simplest molecule that there is. That's the hydrogen molecule, H2. And you'll have your kinetic terms as usual for the Hamiltonian. But in this case, because we have two nuclei, we can't say that one is at the origin. So we'll have kinetic terms for the nuclei, so negative h bar squared over 2 capital M here is the mass of a proton, essentially. And then we have our second derivative for nuclei A and for nuclei B. So the nuclei could be vibrating, for example, and have some kinetic energy. And then we'll have our kinetic energy for our electrons. And we have 2 electrons in neutral hydrogen, so negative h bar squared over 2, and then that's the mass of an electron. And we have the second derivative for electron 1 and the second derivative for electron 2. So we've got 4 kinetic terms. All right, let's think about the coulombic terms. So here I've got a diagram with nucleus A and nucleus B, electron 1 and electron 2. So I would say pause the video now and think about how many potential energy terms there should be. Pausing. 3, 2, 1. All right, so scrolling back up, you can see that I have them all written out here. There's going to be basically the interaction between every pair amongst 4 bodies. So you've got R1A, which is the radius from electron 1 to nucleus A, and R1B, radius from electron 1 to nucleus B, R2A, R2B, and R12, that's the radius between the 2 electrons, and then capital RAB, the radius between the 2 nuclei. So if you just count up all of these lines, we've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 terms. And they all follow Coulomb's law. So you've got negative terms where it's an electron interacting with a proton, so 4 of those. You've got a positive term with 2 electrons interacting with each other, because the negative times a negative is a positive. And you got a positive term with the 2 protons interacting with each other. All right, this is, of course, impossible to solve analytically. So we cannot solve the Schrodinger equation exactly. But one approximation that we will make, which is a pretty good approximation, actually it's a very good approximation, is because the electrons move so much faster than the nuclei, instead of having the wave function be a function of these 4 vectors for electron 1 and 2 and nucleus A and B, we'll treat the nuclei as fixed in space, so a fixed bond length. And later we can account for that using the harmonic oscillator to figure that part back in. But just then we can just say, okay, the wave function for the molecule is equal to an electronic wave function which has just the capital R as a scalar, and then a nuclear wave function where A and B can move. This is an approximation because as the nuclei move, then the electronic wave function will change. But because the nuclei move so much more slowly than the electrons, we can essentially solve the electronic wave function treating the nuclear wave function as fixed. So here would be the Schrodinger equation for just the electronic part for a given bond length. And then we pick an R from solving for the wave function for the harmonic oscillator rigid rotor. All right, so obviously there's going to be approximations with molecules, and we'll talk more about approximate methods after test 2, which is coming up next week. One more thing that I wanted to talk about before test 2, and sorry this page of notes ended up being kind of a mess, but it's kind of a good summary to think about fluorescence and phosphorescence. So the electronic excitations are much higher in energy compared to vibrational, which are much higher compared to rotational. So if we think about, this could be a molecule, yeah, probably a molecule. You can have an electronic state down here, and then an atom could be, an electron could be excited to a state up here, but then within that electronic state you could also have vibrations, and then on top of those vibrations you could also have rotations. And so you've got kind of a ladder on a ladder on a ladder. You got the rotational ladder where the rungs are very close together compared to the vibrational where the rungs are very close together compared to the electronic where it's basically going from one set of ladders to another set of ladders where you go up in electronic. So that's what all of this stuff is up here. The electronic excitation is much bigger than, or the gaps are much bigger than the vibrations, much bigger than the rotations. So what happens with fluorescence is you excite an electron or a system electronically, and then you have relaxation vibrationally or rotationally, and then you emit the light back again, and basically the emission arrow is shorter than the absorption arrow, and so you have this shift towards red. So the light maybe that you absorb is high energy blue, and then the light that comes off is lower energy red, for example. And this is called a red shift, and it might not be blue to red in particular. You know, it might be green to yellow, or it might be ultraviolet to infrared or whatever, but you're shifting in the red direction. That's fluorescence. Phosphorescence is similar, except again you get excited, but then you're going from, for phosphorescence, what a singlet state, and we haven't talked about this yet, so I'll just tell you what it is here. So in a singlet state, all the spins are paired on the electrons, to a triplet state where two spins are unpaired. And this is technically not allowed because we need conservation of momentum. So there's a selection rule, and again, sorry, recall isn't right here because we haven't talked about it yet. But selection rule is you can't lose any angular momentum, and this is just a simple conservation of momentum idea. So the angular momentum can't go away. So you can't have all your spins paired and then have two of them unpaired, because then some angular momentum has just disappeared. And that is technically not allowed, but it does happen in phosphorescent compounds, and the angular momentum is taken up by the surroundings, essentially. But then that process is forbidden, and it's very slow because that angular momentum has to find a place to go. And so that's why phosphorescence is very slow compared to fluorescence, because it involves this forbidden relaxation, and that's where you have things like glow-in-the-dark toys, where you can have, I don't know, maybe your plastic zombie that you put by the light bulb or out in the sun, and then you take it into your room and it glows for an hour or hours later because this phosphorescence is happening, where you have this forbidden process going on. All right, that's it for today, and that's it for this week. Next week we'll be reviewing for test 2 on Monday, and then we'll be taking test 2 on Wednesday, and I'll have more details to follow in the email.